I think we can start now.
Okay, let me share my screen. Okay. Tamer hocam.
Okay. So let's give me 1 minute. Okay, so let's start. Welcome to everyone. Today we will talk about SparseBase and SparseVis. So these tools are developed within the Sparsity project, and the project is about optimization and co-design for sparse computations. So when we say sparse computations, we mean that you probably have a sparse matrix or a network or a sparse tensor. And when we say sparse, it means that most of the entries in your data set either were not observed or maybe their impact on the computation on the kernel that you will perform is negligible or zero. So this project has 5 partners from 4 countries. Koç University is the is coordinating. It's the coordinator or coordinating partner. We have Ines Kaydi from Portugal, Sabancı University from Turkey, LMU from Germany, and Simula Research Laboratory from Norway. The total funding was 2.6 million, and the project will terminate in April 1st. So we are now at the last stages of the project. The funding is from European Union, European joint EuroHPC joint undertaking or European High Performance Computing joint undertaking. And Sinan, I think we can continue.
Okay. Hello, I'm Sinan, and I will talk about basics of SparseBase and then feature extraction part. So here is the outline of the webinar. I will first briefly talk about the motivation behind the SparseBase, then give an overview of SparseBase. After the overview, we will talk about SparseBase modules and demonstrate them one by one. We developed the SparseBase to be a preprocessing library for sparse operations. So what should be understood by that? The sparse operations in SparseBase, we support many sparse data structures, preprocessing utilities such as different reordering and partitioning algorithms and other useful features that can be used in day-to-day HPC or AI or data analytics workflows. So we aim that researchers will not need to implement them again and again for their daily jobs, and so they can focus more on their research by simply using SparseBase in their projects, and that will save them time and ease the work eventually. We use C++ to build SparseBase and heavily relied on modern C++ features, and we prefer to see make as a build system. SparseBase supports different device contexts such as CPU and CUDA GPU, and highly used sparse and dense formats such as CUOs, CSRs, CSCs, CUDA arrays, so on and so forth. And it performs input-output operations such as reading and writing to the mentioned formats, format conversions, feature extraction of sparse matrices, graphs, and tensors, and reordering and partitioning algorithms. There are many many of them we provide support in the SparseBase, and my friends will talk about them more later. I think we can start with the formats. Formats are the heart of the SparseBase. They make many of the operations that can be performed in the SparseBase possible. So they are quite important in this context, and SparseBase supports many formats for both CPU and GPU context. So here you can see the supported formats in SparseBase. So we can basically divide them into three categories, like order one formats, order two formats, and higher order formats. In order one formats, we have arrays, and it is supported by both CPUs and CUDA GPU contexts. In order two formats, we have COO, CSR, and CSC formats. COO and CSC formats have CPU supports, and CSR format have both CPU and CUDA GPU supports. And in higher order format, we use this format for processing tensor files, and it has CPU uh, support as well. And then we have converters. It is another cool and highly useful feature of the SparseBase. So SparseBase allows users to convert their data from one type to another. So we can represent this convergence using a multigraph that can be seen below. We can convert to formats among themselves, and here you can see the supported conversions. Like you can convert order one formats among themselves, and you can convert order two formats amongst themselves. You can see the supported conversions here. And here we have an example code for the convergence. Here we first create a format object from the format base of the SparseBase. Then we specify the types here. Like in this case, we use unsigned long for both vertex and edge, and double for the value. And we pass the reordered file, and we pass the desired format and the context as the CPU context. This is one way of doing the conversion, and another way is can be seen in the second example. So we basically call the as function from the CSC formats, and perform the conversions like that. We can divide input-output operations into four parts in terms of supported files. These are matrix market files, and edge list files, SparseBase file format files, and tensor files. Here you can see the supported input types for each file type. For instance, parallel reading using Pico is supported in matrix market files, and SparseBase file formats, and all of these file types support directed and undirected files, or weighted and unweighted types, etc. And here we have a demo for the for those basic operations work in a real life example in SparseBase. Let's see the demo. Now we are looking at a code example in which we demonstrate how basic input-output operations work and how formats can be easily used, as we mentioned previously. So here we declare two arrays for row pointer and column. Then in a context, we declare a CSR format from format base and pass the types according to the file or arrays we want to process. While creating the CSR object, we pass the sizes of both row pointer and column arrays and then pass to arrays themselves as well. So we're declaring a few variables to show you some basic feature of formats. In the format variable, we pass the CSR objects ID. In dimensions variable, we pass the CSR objects dimensions, and it will be an iterable, as you will see in few lines later. Then we can declare row pointer, column, and values variables, and we can easily access them from the CSR object. So in the second example, we use the file this time instead of creating the arrays manually. Here we take the file name from the arguments and we create a object for that. Then we declare a CO object, and for our CO object, we read our file as COO by using our reader. So the rest are same. So you can see the output of the program, and it shows the format's name as you see in here, and number of dimensions and size of each dimensions. And then in the second example, it reads from a file, and it first sorts the array since it's an unsorted array. Then read the similar things for the file as well. So it concludes our first demo. Now we can continue with the feature extraction part of the SparseBase. Okay. The feature extraction part basically consists of 5 steps. We first need to pass the feature extraction objects that we want to extract from a matrix or graph or from a tensor. It depends on your workflow. Then library determines the fused kernel exists, and then we pass the format that we want to use in this extraction processes, and then we do the extraction as you can see here, and finally the extractor returns a map of features that you passed previously. Like in this example, it returns a map of features of degree distribution feature and betweenness feature. And here you can see the supported features in SparseBase. I didn't put all features we support because there are too many features. You can extract from a matrix or a graph or from a tensor. So now we have a demo for the feature extraction part. Now we are looking at the code for feature extraction. We first define our types and like vertex age value and feature type. Then we define the features we want to extract. Here we use degree and degree distribution features from the feature base in SparseBase and pass the required types. Afterwards, we do the standard reading processes as we saw in the previous demo and define the context as a CPU context. And we first define a variable called engine for feature extraction, and it will be responsible for all the feature extraction related things that we are introducing in this demo. So for example, we can print out the functions registered to feature extractor so far. Then we can easily add or sorry, then we can easily add or subtract features from the engine, and then we can it's possible to catch exceptions in feature extraction in case users try to extract an unregistered feature. So let's add some features such as degrees and degree distribution features. And then we can see the features to be extracted by calling the getList method from the engine object. And finally, we can move on to the extraction part. Here we simply use the extract method to extract the features we have already added to the feature extract engine, and we pass the CO object, a context object to specify to determine where the computation will take place, and it is CPU in this case, and a boolean value to specify if input needs to be converted or not. And it extracts the features like that. Then it returns a map as we saw in the presentation. So let's run the program and see the outputs. Here it prints the registered functions. Then we can see the exception handling in here. Like it says, that feature is not registered in SparseBase extractor because we passed a float type here, so it throws an error for because of that. And we can see the features that will be extracted here from the getList method I show you in this line, and it extracts the features successfully, and like you can see here that the number of features extracted to, and it shows the vertex 0 degree and distribution of vertex 0 here. So it's that simple in SparseBase to extract features, um, uh, and that's all from me. Now comes SparseBase ordering capabilities, and Santiago will talk about the orderings.
Yeah, thank you so much, Sinan. I will
Yeah.
steal your screen share.
Okay.
Okay, hopefully everyone can see the screen. So, hello everyone, I am Santiago, and I will talk a bit about the reordering that is available in SparseBase and how you can use it. So, first of all, going a bit into what is reordering. It is the process of changing the order of rows and columns of our matrix in order to achieve a better structure, to achieve better efficiency, or even memory reduction. And this is very important because it can be used to optimize many sparse matrix operations, such as SPMV and SPMM. And here we can visualize a bit how reordering can change the complete look of our matrix. We can see our sparse matrix, and by applying reordering, we have a completely different matrix, but with the same information. So there are many types of reordering. Each of them target different objectives and have different goals. Some want to achieve a better diagonalization of the matrix. Others want to reduce the amount of fill-ins or reduce the mismatch between non-zeros between rows. And in this context, the SparseBase software library offers a variety of reordering algorithms that target a variety of objectives. And that is why SparseBase is very useful. Okay, so going into the ordering algorithms that we have available, we have 8 that you can currently use: AMD, BOBA, nested dissection, Rabbit, RCM/burn and gray, and degree. And they can be separated into 2 different categories: the ones that have our own SparseBase implementation that were implemented by us, such as Boba, RCM, Slashburn, Gray, and Degree, and the ones that are linked to external libraries. So we use external code that is adapted to the SparseBase library, and we can use it just as the others. For these ones, for AMD, nested dissection, and Rabbit, which are external libraries, it is very important to link, when you compile SparseBase, to link the respective libraries in order to fully use them. Okay, so we have our 8 ordering algorithms, and we want to know what are the objectives that they target, so you know which one to pick. So AMD and nested dissection have a fill-in reduce approach, and they reduce the amount of fill-ins during factorization. If you want a more diagonal matrix, you can use RCM. If you want to for a community search algorithm, you can use Rabbit. And what Rabbit does, it searches communities that are present in the graph, and it puts together the rows and columns that belong to that same community. Then we have Slashburn, that is a matrix compression algorithm, and what it does, it compresses the non-zeros closer together. Rabbit creates a more diagonal block kind of matrix. And then we have other algorithms that have a more not so much specific objectives, such as Boba, which is a lightweight reordering. And what Boba does, it balances the quality of the final permutation with a faster reordering speed. So the quality of the final permutation might not be so good, but the speed compensates for that. Then we have Degree, which orders by number of non-zeros of the rows and the columns. And then we have Gray, which is a very specific and improves branch prediction and locality for SPMV on the CPU. Okay, so what is the input of our ordering algorithms? It is very important to know that most of them operate on the CSR matrix structure, except Boba that operates on the COO. And the input arguments for every ordering algorithm are 4. The first is the reordering parameters, which are specific to each algorithm. Then we have the sparse matrix structure, the CSR structure or the COO structure. Then we send the context. Our ordering algorithms always run on the CPU context. And then we have a format conversion flag that tells you if the input format should be converted to the necessary format. Since most algorithms operate on the CSR format, such as the degree ordering, here we don't need to convert the input format because it's already in the CSR format. And the output is the inverse permutation vector. Is always for every algorithm, it's the inverse permutation vector. What is this permutation vector? Permutation vector is an array that tells you the new order of the rows and columns. So in this example, we can see that row and column 3 go to the first position, then row and column 2 go to the second position, and so on and so on. The inverse permutation vector, which is the one that we output, is the same, but we inverse. So instead of the elements representing the columns and the rows, it's the index. So here, row and column 0 go to position 3, row and column 1 go to position 2, and so on and so on. And this is a way to codify the new permutation of our matrix. Then each ordering algorithm has their own parameters. I won't go into much detail. You can find the different parameters in the SparseBase documentation. But it is important to know that they can be customized. So an algorithm is not does not have fixed parameters. They can be customized to your liking. And it is very important to note that every algorithm with parameters has a default setting. So if you're unsure about about which parameters do you use, you can just go with the default. And then there are algorithms without any specific parameters, and for those you take an empty structure as argument, such as AMD, Rabbit, and RCM. I will show a quick video on how you can apply reordering to your sparse matrices. I'll just remove the sounds. Okay, so here we see a very basic C++ code snippet. We include necessary namespaces that are very often used in SparseBase, and we can start by reading our sparse matrix that is passed as an external argument into a CSR structure. Then we create the context in which our algorithms will run on. In this case, it's the CPU context. And then we call the ordering function. But it's first you need to specify the parameters. In this case, it's the degree ordering. So we send a flag that tells you if we want by increasing order of degree or decreasing order of degree. The function receives the four arguments that I mentioned earlier. The first is the ordering parameters that are specified earlier. Then the matrix structure, in this case, it's the CSR structure. And then the context, and then the same flag. In this case, it's false because we don't need to convert the input format. The output is the inverse permutation vector. And then from here we can see the RCM, which we send a different, the empty structure because it has no arguments. And then we have the gray ordering, which has some parameters. So we send multiple parameters and they all output the inverse permutation vector. And then to apply the permutation to create a new structure, we call the function to permute, and it receives four arguments. The first is the inverse permutation vector. The second is the matrix structure. The third is the context. And the fourth is the same flag mentioned earlier. It is very important to note that the permutation vector is a single array for both the columns and the rows. So some algorithms only apply reordering to the rows of the matrix, and in that case, you need to specify so. So we have a function that only applies the permutation to the rows. And in the others, most of them apply to both rows and columns of the matrix, and you permute both. So this was a short tutorial. You can apply these reorderings to all kinds of matrices. Some algorithms are only available to symmetric matrices, others to not symmetric, but that is extensively specified in the SparseBase documentation. And now the reordering module is over, and my colleague Beza will talk a bit about the partitioning capabilities of SparseBase.
Thank you, Santiago. Now I will share my screen. Okay. So hello, my name is Beyza. Today I will be talking about the graph partitioning tools under SparseBase. And specifically, I would like to show some demo about MTK par graph partitioning. So why do we need graph partitioning? That is an important point. For just large-scale graph optimization problems, we will need to chop the graph into pieces because sometimes the graph can be too large to fit into one machine. So we will first compute under different parts, and then we can stitch the results together. But that depends, like the quality depends how we partition the graph into pieces, as you see in the image. There can be some optimality from interaction between different pieces. So that is why we would like to have a small cut size, and meaning that links between different groups should be less to reduce the network communication costs. And we can partition graphs and hypergraphs. Graph is just, there is an edge between two vertices, and in hypergraphs, like an edge can consist many vertices, as you can see in the downmost image. So for SparseBase, for now, we can support many partitioner tools. For graph partitioning, we use Metis and MTK-par. At the same time, for hypergraph partitioning, we utilize PATOH and MTK-par. So when we come to MTK-par, this is actually multi-threaded call to have hypergraph partitioner, but this can also partition graphs. It's a parallel algorithm. That means like it's really fast and high quality. And it tries to, while this partitioning, at the same time, it tries to minimize certain criteria related to the cuts I talked previously, meaning the connections between different partitions. So why is MTK-par is good to use? Because like performance-wise, there are some sequential partitioner algorithms. But if with only 10 threads, you can perform 10 times better using this partitioner tool, which is available under SparseBase. For scalability, you can use like a large number of threads, up to 64 easily. For deterministic, which means when you give the same input, you will definitely get the same output. Large K partitioning means like you can partition the graph into a large number of blocks. You can like optimize graph partitioning. You can map hypergraphs into graphs. And also for some parts, you may say, okay, let me put some vertices into some groups, fix them there and distribute the other ones. So you can also do fixed vertices. I will not go into technical details, but I put the reference in the at the end of the page, which is the MTK-par's GitHub page. You can check there. Why I put this is like when I show you demo, you can work with different objective functions. Like you can try to minimize cutnet metric or connectivity metric. There are several of them, and we can give them as parameters. So all you need to do, as I said, this is already in SparseBase. So you need to install MTK-par, and then you will just, under the build, you need to give the library and include paths. And then when you make, you will be able to use it. I put already an example tutorial under SparseBase build examples MTK-par partition. You just need to run it and give it an input file. I will show you a quick demo how we can do this. So as you see here, we are under SparseBase, and if you go to build, examples, and MTK-par partition, now we can see the executables here. We will just execute it with the data view edge list. But before going into that, like I would like to show some parts in the code that you can play around. So this is the code we are running actually. This is the example tutorial. As you can see here, we have a function has ending that is actually checking is this an MTX file or UH list file. So according to that, it will call the readers. As you see, we take the file name as input, and then we use the has ending function to check if it's MTX or not. So we have two formats, coordinate and CSR to read. If it is MTX or not is checked here. So as you can see, if it is like edge list reader, it will just read like to edge list reader. And then if it is MTX, it will call the MTX reader. And then the reader will read into coordinate and CSR formats. Then all you need to do is call the partition wrapper we created over MTK-par, giving the red formatters like coordinate and CSR. Then we can use something like that to see if the partitions are consistent after the partitioning is done. Also, this is the source code where we utilize the MTK-par partitions. You can find it like under source partition and MTK-par partition. Here, as you can see, there are many other functions you can use. For this tutorial, I use these ones. There's, as you see, like there's create graph, and then we partition the graph, calling mtk parse function, and then we get the partition. And as you see, we can compute several metrics like imbalance cut, and we can get the partitioning results. And also in the header file shown here, there are parameters. You can change the parameters here. For example, there is the imbalance allowance, like we allowed 3% imbalance here. And there is, as I showed, objective function. We are now choosing cut metric minimization. So we said cut, but we can use others. Let's see the output. As you see, your edge list is red now, and yes, if when you see the results, like it gives the partition results, I just printed 10 of them. And then, just a second. Is there a problem? Just a second. So you see the results, and there is the imbalance showed that is under 3%, and there is the cut metric calculated. And we can also calculate read MTX file. I gave input MTX to read. And as you see, it can also read MTX reader, and then it gives the partitioning results again. So this is all from me now. Thank you. Now, Kameraja will continue with SparseVis.
Hi everyone again. So I will talk about SparseVis. So this is another tool again built within the SparseVis project. So these are the current developers. So Denis from Sabancı University, Santiago is from INESCAID, and me again from Sabancı University. So you can find, in fact, all the tools, all the codes here under the Sparsity EU project GitHub page. So SparseBase is here, for instance, and we also have SparseVis here. So we have a documentation for the tools. This is the SparseVis documentation, and if you go back for the SparseBase again, you will see the documentation and also extra tutorials that shows you how to do simple things with these tools without any complicated coding. In fact, complicated things with simple coding, maybe that's better wording. So let me go back here. Okay, so this is the current state, and you will see some configuration files, and I will tell everything about this in this webinar. So for matrix processing and tensor processing, we are working with config files, and I have the before maybe I can talk about that. So SparseBase, as you already know now, is a preprocessing library that puts sparse operations at the forefront, designed for HPC, data analytics, artificial intelligence, and aims to ease the work of developers and researchers. So SparseVis is also trying to make the works of researchers and industry people easy, but it is an ordering focused sparse matrix and sparse tensor visualization and performance profiling library. So it is using some of the codes from SparseBase, in fact. So let me start with the live demo. So let's start with matrix. So we have this config file here. Let me first initiate the config file, and after that I will talk about what things here mean. Config matrix. Okay. So, okay. The configuration file name is not correct. Okay. So here we have something working here, and let me go through these things. So everything you create in SparseVis is saved to your disk in a binary format, in a space-efficient format, so you can reuse them whenever you want. Whenever you run it again, everything will be read from the disk in a very fast way. And also for really large tensors, for instance, we are using parallel I/O libraries, so you can also read these things in a fast way. So you need to specify a couple of folders, the project folder. After that, where are your matrices, where are your orderings, or where do you want to put the orderings? And where are the visualization files generated? Where do you want them to be again? So this is the resolution of the visualization. I will also show you a couple of examples. So here is a matrix. We obtained it from our partners, Simula, in fact. So this is from some cardiac simulation. And we are applying these kind of orderings. So there are also other orderings available. Every ordering has its own characteristic. In fact, Santiago talked about them extensively, and you showed some figures there. Here is a live demo of that. And as I told you, SparseVis also can do some kernel profiling. So you implement your kernel inside SparseVis code. And after that, you say, I want to try it with that many threads, with that many scheduling. And after that, the scheduling chunk here, number of iterations that you want to perform, and number of iterations or repetitions, in fact, or executions you want to ignore. So we ignore a couple of first iterations. You can do it from here, and you can also implement GPU kernels with CUDA, and everything will be handled by SparseVis. You just need to implement your kernel, maybe 5 lines, maybe 10 lines, by extending our GPU kernel class or CPU kernel class, and it will be executed. So let's check the output. So here I said that let's do it with 16 threads. So every ordering here is performed in parallel. So you don't need to wait for one. And after that, they are written to binary files. And after that, these kernels are executed. So at the end, so I wanted to see my files here, matrix visualization files. So where is that here? And if you open that, you see this. So this is the original natural ordering of the matrix. And here, I told you that when we say sparse, we mean that most of the entries are 0, or maybe they are not observed. So these white spaces shows those places. So we don't have any observation, any numerical value, anything here. Okay. So only the red ones are full here. Okay. And the darkness of the red here. So if it is darker, or it means that there are more non-zeros inside. If it is lighter, there are less non-zeros inside. So originally, it looks like most of the non-zeros are close to the diagonal for this matrix, and it is expectable because this is coming from a physical simulation, and usually this is the pattern that you see. Here we have some statistics. These statistics are some of them are coming from the literature, and some of them are our inventions, let's say, and they are mostly related with the cache usage. They are mostly related with the distances in between these non-zeros, because when you make them closer, so it is good for some kernels, okay, like sparse matrix vector multiplication here, for instance. And this thing shows that the non-zero distribution of the bins, so if the number is large here and if it is shorter, so if this length is shorter, as you see, most of the bins here are 0, and we have 64. We divided the row space and column space in the 64, so that was the resolution. In fact, you can increase that or reduce that to have better or more generic observations. And so this is another ordering, approximate minimum degree, and it creates that kind of matrix. So this is gray ordering. It tries to put similar rows together. So if you assign that set of rows to a single processing unit, single core, then the cache will be more comfortable to use. So this is rapid ordering. This is designed for graphs mostly. It tries to, again, make similar rows and columns together, but it tries to, in fact, construct regions like these, which are very dense. So this is dynamic minimum degree. So you remove the larger dynamic degree, in fact, so the larger one, but it looks like this is not a good one because, as you see, most of the beans are full, unlike here, and only we can have like, so this is good, in fact, 100K. So this is only 10K. So it means that there are beans here which contains like 100K non-zeros, but here the number here is only let me see. In fact, no, we have like 333K. So I was a little bit mistaken. So here the top is 62,000. Here the top is 300,000. So this is in fact better. So this tool in fact is useful for this purpose. So you try to understand if you could cluster, if you could make similar things together. So this is another ordering, for instance, and that looks perfect for that purpose, right? So everything is now closer to diagonal, and this is desirable. So as you see here, most of the beans are empty, only a couple of them are full, but on top so in terms of the maximum non-zeros in a single bean, as you see, this is similar to this one, okay? So these are other ordering. So every ordering here can be useful for some other kernel. For instance, this one, it looks like the performance here is 006056. So this is GPU kernel when you run this SPMV on this ordered matrix on the GPU. So you have this much runtime, but as you see, it is better here for the rabbit ordering, or it is better here for the RCM ordering for the regions I stated. So this is the matrix version, and I also told you that we have the tensor version, right? So this is tensor. Let me open also this. So I have two tensors here. Tensors can be multi-dimensional, so we can have like 6 mode, 7 mode tensors. And the first functionality of SparseVis is since this is a visualization tool and visualization is easy and practical in 3 dimensions, so you choose 3 dimensions, arbitrary 3 dimensions from your tensor, and after that you state them here, and this tool extracts only that view, okay, so that modes from the tensor file, and after that work on that. So again, similar settings must be done, and you just need to change this to tensor. So it will execute these orderings. So we extended all the graph orderings, all the matrix orderings to tensors now by generating a 2-dimensional structure from the tensor. So you can follow that in our article. But maybe it's better if I start from this mode. So this tensor mode is generating the outputs in for each tensor. Okay, for each tensor you stated here, there will be an HTML file having all these orderings. Okay, so let's see what do they create. Again, kernels are executed. And this thing, Kamer tensor random node loop is HTML is generated. So this one, for instance. So this is a tensor. I generated it by using some pattern, some diagonal pattern. And after that, I randomized I permuted the dimensions randomly. Okay. So this is actual aspect ratio. So this is actually a tensor like that. So this is like 1,000 to 1,500 maybe. No, 1,000, 2,000, 3,000, 3,000 tensor, right? Okay. So this is the original one. So this is the one in the file. But if you apply the algorithm, the ordering algorithm, it in fact kind of inverts, okay, the random permutation. So it generates the original file. So these are this and this. Okay, so this and this are the same tensors, in fact. Okay, same data structures. But as you may guess, so if you If you use this one, for instance, on some kernels, because of this property, so you only have these beans full, you will have less execution time. So other ordering, so this is something new. I don't know if there is a counterpart of this in the literature. So other orderings that we have, and their extension to tensors generate different patterns here. So AMD is similar to RCM. Bobo ordering, which is a recent one. It is very lightweight. It is in fact one of the things Santiago implemented. So this thing is generating something like this, and this is slash burn. It's an old one. It generates some pattern like this, and this is the gray ordering. Okay, what else? So this is tensor dimensions. Again, this is a synthetic tensor, and in fact, you can have also, you can homogenize the aspect ratio, and you can use the same length for every dimension. And this button will switch that immediately for every tensor here. And these are the looks from the density of the non-zeros when you look from one, like these two axes, for instance. Okay, so this is YZ. Okay, so this is similar to this one. And if you add the non-zeros on these fibers, you will have a pattern like this in terms of non-zero distribution. And since we have 3 dimensions here, we have 3 figures here, 3 choose 2. And this is the value distribution. So we did the same for the values inside these tensors. And if you add them up, you will have this density. If you add their absolute values, in fact, you will have this kind of density. And this is a synthetic tensor, and this one here is the NIPS tensor. So this one is a real-life tensor. In fact, it is related with the publication pattern of the authors on NIPS. Some dimension is years, and these are the dimensions 0, 1, 2, if I'm not mistaken, and this is the original tensor, okay? So this is not synthetic, this is not randomly permitted, this is the original one, but when you order that, most of the non-zeros, as you see, they go to here, and there are many empty bins here. Again, if you do some computation on this one, like something to, for instance, decompose the tensor for compression or using machine learning, so you will have this pattern, and that decomposition will take less time. So other orderings give these kind of things. Okay. What else? The one final thing I want to show is, so we do not only support 3-dimensional tensors, we also support other more dimensional tensors, which are more practical, which are more common in real life. So this, for instance, this full tensor mode does that for us. So you just need to change the zoo type. Zoo means that we are grouping the things on a single HTML with respect to something. So tens means we are grouping the orderings with respect to tensor. You can also do the same with respect to ordering or with respect to full tensor. So if you change that and run the same thing here, give us just 1 second. So these are now done. And after that, kernels are executed, kernels are done. So this thing generates the views of that NIPS, for instance, this guy, okay? So this is already 3-dimensional, so there is nothing exciting here. But so these files are more exciting. So if you, for instance, open, I don't know, RCM NIPS full here, and you see that, so this tensor is 4-mode tensor, so there are 4 dimensions, and there will be 4 out of 3, so 4 views, because every view is, okay, so every view is choosing 3 dimensions. So these are the 0, 1, 2, and these are the length. So the last dimension is only 17. The last mode has only 17 length. So this is why, in fact, if you try to visualize that, oops, you have something like this. Okay, so this is the view. If you try to visualize 2000 times 2000 times something like 10, the same pattern also arises here, and the same pattern is also arising here because of the final dimension is only 17. But the full tensor mode computes the two-dimensional structure from four-dimensional tensor now. So instead of the three-dimensional to two-dimensional conversion, now we are using a four-dimensional to two-dimensional conversion and apply the algorithm on top of that. So I think this is all about SparseVis. And let me go here and on behalf of every panelist here. So if you have questions, you can ask.
I think there's one question in the Q&A box. Does underlying hardware affects the feature extraction?
Sinan, do you want to answer that?
Yeah, sure.
Okay.
I don't think that it will affect the result of the feature extraction, but maybe you can accelerate the process.
Okay, thank you. So if you have any questions, you can use the Q&A part. Okay, I guess there is no other question. So I would like to thank to all speakers for great talks and valuable contribution to today's seminar. And thank you all for attending this event. So see you at the next event then. Have a nice day.
Thanks for the organization and moderation, Özlem Hanım.
Thank
Yeah.
you. Bye.
Bye.
Bye bye.
Bye.